Hello everyone, my name is Jack Smiley and I am a sophomore at Lehigh University majoring in electrical engineering. This brief presentation is meant to explain the research I am currently conducting under Professor Javad Kazai and the Lehigh University Integrated, Resilient, and Intelligent Energy Systems Lab. My research is centered on electrical power systems, and for the past semester has focused specifically on DC-DC boost converters, their design, and their applications for solar energy. This is currently a topic of great importance, as climate change is worsening every day, and more efficient renewable energy systems are going to be needed to combat this. One area of renewable energy that shows great promise is solar energy, which is typically extracted through the use of solar panels. Figure 1 shows the electrical hardware that exists inside of a solar panel. Solar panels are composed of dozens of smaller solar cells. These cells are primarily composed of silicon, but are also doped with other elements such as boron and phosphorus. This doping creates a separation of charge, which in turn creates an electric field. When sunlight hits the single solar cell, the photons have enough energy to break an electron off of some of the atoms making up the cell. The electric field then pushes the electrons toward one side of the structure. In other words, a current is created. This current can then flow through the metal contacts on each side of the cells, creating a voltage difference. This voltage is small, but when combined with other cells to create a panel, the size of the voltage can increase drastically. For example, a standard household solar panel, depending on the exact size, can typically generate 20 to 40 volts. However, the outlet supply in American households is 120 volts at a 60 kHz frequency, so the voltage must be both boosted and inverted to alternating current. To do this, the boost converter first boosts the voltage to approximately double what the final AC value will be. This is to account for losses that occur during the inversion process. The inverter then transforms this voltage into alternating current, which is finally ready to be sent into the grid. Throughout this entire process, devices like MPPTs, or maximum power point trackers, and closed-loop controls are being used to ensure that this process is maximally efficient and appropriate for the current weather conditions and power requirements. Figure 2 shows a real boost converter on a breadboard consisting of an inductor, a semiconductor switch, a Schottky diode, a capacitor, and a load and switch gate resistors. When a voltage is applied across the converter, current begins flowing through the inductor. When the semiconductor switch is closed, this current flows directly to ground and a charge is built up within the inductor. When the switch opens, the inductor pushes current through the diode and into the capacitor, building up charge and voltage within the capacitor. The output voltage is the final voltage across the capacitor and load resistor. In real-life systems, the semiconductor switch is controlled by a PWM, or pulse-width modulated signal, applied to its gate. The duty cycle of this signal, as well as the value of the converter components, dictates the operation of the converter. Figure 3 displays some typical PWM signals. The first signal, which has a duty cycle of 10%, is high for 10% of its duration and low for 90%. The signal below has a duty cycle of 50% and is high and low for 50% each. Figure 4 shows the actual boost converter schematic that was used for simulating simulations. It includes a closed-loop control block that dictates the behavior of the switch. The closed-loop control block works by using an adder to calculate the error between the current voltage output and the desired output. This voltage is then amplified and sent to a PID, or proportional integral derivative controller. This controller works by summing the current, accumulated, and future predicted errors and sending that to a PWM generator. This generator sends a PWM signal to the switch's gate, which controls the behavior of the converter. The converter is then able to respond to changes in both the energy requirements and the weather conditions in real time to supply maximally efficient power. When testing this converter in Simulink, the component values and switching frequency can be chosen based on the equations on the right side of the PowerPoint. The PID controller needs to be tuned appropriately. This can be done using the Ziegler-Nichols tuning method. This method works by setting the initial proportional, integral, and derivative values to 0. The proportional value is then gradually increased until the output voltage oscillation is stable. The final derivative and integral values can then be calculated using the equations in Figure 5. The results are shown in Figure 6. A constant input voltage of 9 volts was able to be boosted to a steady 18 volts using a 50% switch duty cycle. The Simulink tests were then used to create an actual boost converter to test in the lab. The converter from Figure 2 was used, and a pulse generator was used to control the switch, as no PID controller was available. Using the same principles used for the Simulink design, a constant input voltage of 4 volts was able to be approximately doubled to 7.94 volts using a 22% duty cycle. Typically, a duty cycle of around 50% is required to double voltage. However, the exact component values found from the calculations were not available, so the parameters had to be modified accordingly. Although this circuit seems small and simple, it is very important to the operation of solar panels and the impact of solar energy as a whole. They allow for maximum energy efficiency based on energy requirements and weather factors, and when used in conjunction with MPPTs and closed-loop control, can even allow for the storage of excess energy for later uses. Proper boost converter function also protects the downstream components within the panel from burnouts and other issues. This helps to maximize both the performance and lifetime of the panels, saving the users money and keeping as many panels in the grid as possible. When all of these processes are optimized, our reliance on harmful, unsustainable energy sources can be minimized. I would like to thank Professor Kazai for his mentorship on this project, as well as the other members of Lehigh's Integrity Lab. Thank you for listening.